And off you go, Chris.
Okay. I suppose I need to say I'm going to continue with the meeting. Cool. So thanks, Sam, and everybody for inviting me, and thanks for attending this talk. Yes, so I'd like to talk to you about some work joint with Shimon Urbas, who's actually a PhD student of mine, but he took some time out to be a PDRA to help with this. And Matt Ludkin was in on when we had some initial discussions on this. And yes, the Apogee-to-Apogee path sampler, which is kind of an alternative to HMC and NUTS, which I think brings out the best in both of them. Well, I'm going to say that, of course, but I'm quite enthusiastic about this one. So let's just start with the setup. So standard setup for example, HMC. We've got some target distribution, some posterior pi of x, which we'll think of as e to the minus some potential. Okay. We're going to sample momenta over and over again. Everything I'm going to say today, I'm going to use the identity matrix, but it all follows through the same with any positive definite mass matrix. It's just messier notation. So I'm just keeping the notation simple today. I am actually making assumptions that people are familiar with the basic MC-MC setup. So I deliberately removed a couple of one slides on Bayesian inference and so on. But so please do jump in if I've made too big an assumption. So in HMC, we have an extended target. I'm going to call this pi tilde, which is a function of position and momentum. And its negative log is essentially the potential energy plus the kinetic energy, half p transpose p. Okay, or you can think of that whole thing as the Hamiltonian total energy. A few bits of notation I'm going to use. I will remind you about these, but so the position and momentum is really what we're thinking of as a point, and that's, I'm going to call that Z. And we're often going to be flipping the momentum. So I'm going to call Z minus the same as Z, but with the momentum flipped. I'm going to write pi tilde of Z for pi tilde of XP. And obviously, if you flip the momentum, then PP transpose hasn't changed, or P transpose P hasn't changed. So the pi tilde is the same. Okay. So HMC, in case you've not looked at it in any detail, here's a quick heuristic of what it's trying to do. You're at a current point. I've given that a big black splotch here, and I've done a two-dimensional target, and these are the contours of it. So the potential is larger further out in the tails. I think this is a Gaussian of some variety. So I'm at the current position, and I've got a tuning parameter T for the moment. And we're creating a proposal that's going to be this X. And what we're trying to do is, from this current point, we sample a momentum, P current, from normal naught times the identity matrix. In this case, in general, you'd have a mass matrix. And then we integrate Hamiltonian dynamics, just your standard frictionless dynamics for a time T. And that's what's happened here. So you can see the momentum is obviously initially pointing down and to the left in the diagram, and it goes all the way down to the bottom of the potential, back uphill, around, back downhill, uphill, and so on, until it reaches this. That's what took time T, whatever T I took, and that's our proposal. And the point is that if we'd integrated Hamiltonian dynamics exactly, then the total energy would be the same, your pi tilde would be the same, and because Hamiltonian dynamics is a transformation with Jacobian of 1, you've actually got an acceptance probability of 1. So that's what we're trying to do, but you can't in general integrate the Hamiltonian dynamics exactly. So here's HMC. And it actually has two tuning parameters. So you've got your time, T, or in a step size, essentially. So a numerical integration step size, epsilon, number of leapfrog steps, L, and the product is your total time. So you do L steps, each of time, epsilon. One iteration of HMC, given your current starting value. So I guess you're probably all familiar with this, but I'll go over it just to be sure. Sample a momentum, let's call it P0, and set my initial full coordinate, position and momentum is my current position and this momentum. And then we use a numerical integration step. Usually we use one called the leapfrog step, but I'm deliberately not going into the details of leapfrog because actually any other step with a couple of key properties would work all the way through this. So it's not specifically you have to use the leapfrog. So we do, leapfrog is a just simple numerical integration to take you from a position of momentum at time I-1 to a position of momentum at time I. And we do that L times, and we take this final position of momentum as my proposed Z. And I've got my current Z, and my Metropolis Hastings acceptance probability is minimum of 1, and to make it a probability, the ratio of the extended targets. Okay, so with that probability, we say, yes, let's update. Otherwise, we reject and stay where we are, and we throw away the current momentum, ready to start all over again for the next iteration. So that's HMC. It's approximating. Obviously, if the pi tildes, if energy was conserved, this would be an acceptance probability of 1. What's the leapfrog step? Well, I'm not going to say the details because all we need is these 3 facts. It's deterministic, right? If you, at this position of momentum and you leapfrog step for time 0.3, then you'll always get the same result. It has a Jacobian of 1, just like Hamiltonian dynamics. And if you're at a current position and you leapfrog and you get Z at the next position, then if you flip the momentum at this next position, right? So point it in the opposite direction and do a leapfrog step from there, you get back to where you started, except the momentum's flipped. Okay? Or, yeah, equivalently, exactly what I've got here. So I've been talking with Lionel recently, and actually I think we might be able to relax the deterministic thing, but you have to be quite careful about how you attach any randomness to the leapfrog. So let's keep it simple here. Yeah, deterministic is usually implicit, but it's certainly to understand the basics of the method, it's necessary. And I've already said that your total integration time is L times epsilon. So here's just an approximation to the exact dynamics, or close to exact dynamics I showed you last time. I've got sorry, you can see all this coming out. I've got 50 leapfrog steps, step size of 0.1, so time is 5. Here's my current point. Here's the leapfrog steps going all the way around to this proposal. Now, the property 3, which says if you're at some point and you flip the momentum and do a leapfrog step, you get back to where you were, but with the momentum flipped. That actually means if I start at the end point and flip the momentum, I apply all those same 50 leapfrog steps, I would get back to the black splodge, but with the momentum flipped pointing the other way. And in fact, it's not just that. All the circles will be the same in terms of their x coordinate, the x position, and the momentum would be the same as it was on the way out, but with the momentum flipped. So everywhere, it's the same. And indeed, to put a spoiler ahead, if I started here at this position with the momentum that the trajectory has here and integrated forward, I'd still get to the x. And if I integrated backwards in time, I'd get to the splodge. Okay, HMC has some well-known tuning issues. So this is for, it's like a banana target. So it's 40-dimensional. And every pair of dimensions, every odd and even numbered adjacent pair, have a banana shape. Right? And it's dimension 40. Don't ignore the bottom half of this graph. What we've got is epsilon along the x-axis and L on the y-axis. Just take the value, the positive values for now. And then we've got a measure of efficiency as a function of each of those tuning parameters. Very grateful to Shimon for producing lots of graphs like this. And yellow is high efficiency, blue is low efficiency. And what you can see is that for a particular, essentially T, because it's like L is proportional to 1 over epsilon here. So for a particular integration time, you're pretty efficient. But if you step off that integration time, efficiency plummets like you stepped off a cliff. Or similarly, either way, for a particular epsilon value, efficiency plummets. If you choose the right L, fantastic. If you choose an L, number of leapfrog steps slightly off, then your efficiency just drops massively. Now, on the bottom, we've got something which actually cures that to an extent. It's in Radford Neal's HMC chapter of Handbook of MCMC. Every iteration, you've got a T, which might be 5 seconds. Every iteration, you jitter that and you actually sample something uniform that's about T, but could be a little bit below or a little bit above. And that's the integration time you use for that particular iteration. We are calling that blurred HMC. And if you do that, you can see it's much smoother on the bottom, but still, and in fact, the optimum efficiency, we could get HMC to be more efficient using this blurring in this particular case than if we didn't use the blurring. And the optimal value is here. Shimon has nicely marked it on. But again, if you step too far off, if you get L wrong, oh, sorry, that's what the bottom half is blurred. So negative L is just saying it's actually 20 leapfrog steps, but you're doing this blurring. Right? But either way, HMC, basically, it can be really efficient, but you have to get your L epsilon combination just right. So here's the start of the solution. I've drawn that exact same path from the black point to the proposal at the blue triangle, but I've colored in chunks that I'm going to call segments. So here's where we start, and the momentum's pointing in the direction I'm taking the cursor. You can see it goes downhill, then it starts going back uphill, up the potential. Here it reaches a local maximum in terms of what the potential is along its path at the final, or between the last black circle and the first red upside down triangle. Then it starts going downhill again, then it goes back uphill, reaches another local maximum, which in reality would be somewhere between where the red ends and the green starts, and so on. So what I've done is partitioned the path according to where local maxima in potential happen along the path. Now, that is a definition that's invariant to which direction I'm going. So if I were to start at the blue triangle, right, I would still be going downhill, back uphill, get to a local maximum somewhere between the last blue triangle and the first pink or purple or whatever, magenta diamond. All right, so it doesn't matter which way you're going. This is the same way of getting a sort of partition. You'd always get the same partition. To make it formal, right, imagine you're looking at the momentum in the direction of the gradient. Then whilst you're still going uphill along the path, that would be positive. And when you're going downhill, it will be negative. So your true maximum will have occurred somewhere between the two, or we can think about that happening. So if you have two of those points, XA and point XA1 and XA2, where that's happened, then the segment is from when it starts going downhill, so A1 plus 1, PO, to the end of the final point where it's uphill before it starts going downhill again. Yeah, so this is just the maths for exactly what I showed you in the picture. And I'm going to say moving backwards in time from position X with momentum P, that's the same as just moving forwards in time from position X with momentum minus P. So I would get the same set of segments if I started somewhere in the middle and traveled some steps forward and the rest of those steps backwards. So let's just see that. So suppose I started at, I don't know, this green plus here. And I went backwards in time, then the whole thing is deterministic. So I would see exactly the same set of segments going backwards as I do. And if I integrated forwards, obviously it's exactly the same process as before. I would see the same set of segments before. So it doesn't matter where you are in the path. This is where, in terms of position and momentum, you will always see the same deterministic path and you will see the same set of segments. So let's start with straightforward segment 0. So segment 0 is I simulate forwards until I reach the first apogee, and I simulate, an apogee, sorry, is where it's at its peak. So, and I simulate backwards until I see the first apogee. And segment 0 is all those points in the segment that includes the current point. So if I go back, oops. So here I've simulated forwards, so it'd be these black points, but I'd also need to simulate backwards until I hit a maximum, which is probably going to happen fairly soon. Yeah. And vital thing, the whole thing is deterministic. So if I pick any other point, so Z0, remember, is my start point. If I pick any other point within that segment 0, and I find the segment 0 for it, it's going to be exactly the same set of points, set of positions and momenta. Let's see that. So in fact, here is my entire segment 0. Here's my current point, going forwards, going backwards until it hits apogees. If I were to pick this point and integrate forward, I'd see all these, and then I'd stop, and this position and momentum. And if I go backwards, same. Yeah. So it doesn't matter where you are in here, you'll produce the same, exactly the same set of positions and momenta, and you'd stop at the same places because they're at local maximum. So here's a simple version of the Apogee-to-Apogee path sampler. It's not the one in the paper, but we'll get to the one in the paper via this. So we have a step size and just that single tuning parameter, and we come up with some weight function. So Z, you can think of it as your current value. Z primed is your proposed value. A natural simple weight function, the first one I tried, in fact, is that it ignores where your current value is, and it's just the extended target in your proposed value. So that's an idea of a weight. It just has to be a non-negative function of Z and a current and a kind of proposed value. So we're at X naught, just like HMC, we're going to sample a momentum. All right, we're going to time step forwards until the first apogee, time step backwards until the first apogee going backwards. Propose one of the points in that segment at random with probability of proposing a particular one proportional to its weight. All right, so it might be just proportional to the extended target at that particular proposed value. And accept it with this probability. We'll see exactly why this is the right one on the next slide. Notice, however, already that if I had the weight as just the pi tilde, the extended target, then we've got pi tilde z prop and pi tilde z prop on the bottom here, cancelling. Similarly, pi tilde z current, cancelling with this. And this is a sum of things that don't depend on the current or proposed over the same set of z's. So the acceptance probability is 1.
Okay. I'm sorry, can I ask a question?
Sure.
So I didn't get what is the definition of Z prop, sorry.
So Z prop, so I've got here, I've got a whole bunch of Zs, my current one and all these other ones, including the current one along the segment. I'm going to choose one of them at random to be my proposal. And which one I choose is, so going to be at random. The probability of choosing this one is proportional to the weight here. So pi tilde, the extended target and the momentum. Okay. So that's my proposal. It's a random one of these. Thanks for asking.
Thank you.
Is that clearer now? Yeah.
Yeah. Thanks.
Cool. Okay. So let's see why that is the right algorithm. Oh, firstly, sorry, here's an illustration. So I've actually proposed this one. That's all it is. So we want to show that the probability of being at Z current when you're stationary, proposing Z prop and accepting it is equal to the other way around. Probability of being at Z prop, proposing Z current and accepting it. And that's the same as showing that this whole expression is invariant to me switching around prop and current. Well, let's just write it out. So pi tilde Z current, this is your probability of choosing a particular one as your proposal. Yeah, it's proportional to the weight, so I'm just normalizing it, so it becomes a probability. And here's my acceptance probability that I had on the previous slide. All right, and you can see we've just designed this acceptance probability exactly so that when you multiply it in, these could probably be curly brackets to help, then you have on the left side of the minimum the same as on the right side, but with the props and currents switched. So it satisfies detailed balance. Now, what was hidden in that is whatever proposal I choose from that segment of my current X and P, if I find the segment 0 for that, it's going to be exactly the same. So from Z prop, I would also have this same S0. This is absolutely vital to the algorithm being correct. Yeah. From this X, if I were to integrate forward until the next apogee and backward till the next apogee, I'd see exactly the same set of X's and P's, which is why we choose apogees as the thing. Okay, so that's apps 0, just using a single segment, the current one. But it might not be enough because your target might be quite elongated in one direction and not in the others. So let's bring on apps K, where we're going to use K+1 segments. Apps 0 uses 1 segment, apps K will use K+1. So you've got to be slightly careful how you position these K+1 segments. And there are multiple ways of doing this right and an awful lot of ways of doing it wrong. Okay, one of the ways of doing it right is what I'm going to describe here. We did try another way, but it wasn't as robust. So you've got K+1 segments here, and you've got your current segment, which you can work out. And you want to decide where your current segment lies in these K+1. It could be the first, it could be the last, it could be somewhere in the middle. What we do is choose it with equal probability of being any of those K+1. And we can call the concatenation of those segments S from A to B Z current, where A might be, I don't know, if you're doing 5 segments, A might be -3 and B, or 6 segments, so K is 5, A might be -3 and B is 2. So you're going 3 segments back, 2 segments forward, plus your current segment. And obviously it could be anything from 0 to K or -K to 0. Everything else kind of carries on the same. So you've got a leapfrog step, a momentum, you do your leapfrogs forwards until you've hit the right number of segments going forwards, and backwards until you've hit the right number of segments going backwards. That's a random thing, yeah. We've got K+1 in all, but we don't know how many of those will be going forwards and backwards. We just sample that uniformly at the start of each iteration. We have the same form for the acceptance. So we still, propose proportional to W, probability. Same acceptance, probability, except now you've got to add up all the Zs in the entire set concatenation of segments and discard the momentum at the end. And as I've put here, yeah, other valid schemes are possible. So here's an example. My segment 0 is as it was before. Here's my segment -1, that's 1 backwards. And here's segments 2 and 3. So this is apps with K equals 3. But another iteration of this, and in fact, it might have been black, and then I had 3 segments going forwards. Yeah. Why is this valid? Well, we only really need to understand why the extra little bit is valid. So point is, let me go back. I choose a proposal. So here's my current. I choose a proposal. There's 1 in K+1 chance of me choosing this alignment rather than the current being earlier or later. Suppose I choose my proposal is one of the green ones. Well, the alignment I need to be able to have exactly the same scenario as this is basically my current segment is the furthest forwards, and I just go backwards. But that also has a probability of 1 over K+1. So to get backwards is the same as to get forwards. It's just a different arrangement, but because we've chosen them with the right probabilities, we're fine. That's it, really. So what about this weighting function? I did pi tilde. All right, that's the obvious one because it leads to an acceptance probability of 1. So this is just choose from all those points that you've got with probability proportional to the extended target. But another one is square jumping distance. You might want to say, hey, I want to choose points that are further away from my current one, more likely. All right, so you might still want to vary it, not make it deterministic, but choose points that are further away, more likely, or combine the two. Okay, because pi tilde comes in the acceptance probability. So you certainly, there's a call for having that in there. If you've got a massive variation in the total energy, and it happens to be really low round where the squared jump distance is really high, then it's not going to be sensible to just use squared jump distance. Similarly, you might want to use absolute jumping distance. You could carry on forever with this. One other thing we looked at was this flip move. So maybe the picture is easiest to explain this. You've got a pi tilde at every single one of these points, total energy, e to the minus total energy. We could find a cumulative sum starting at the left and going forwards. This will add up to something. If we half it, then that will give us a point halfway along according to the sum of the extended targets. And what we do is we flip. So if the current position is in the left-hand half, then we only sample from the right-hand half with probability proportional to pi tilde still. And providing you're careful with what happens in the middle, this still satisfies detailed balance as well. And it's obviously guaranteed to move you often quite a bit more. So those were the 6 things we looked at. You could have looked at loads more.
Is it, can you view that last one as being a bit like the over relaxation in Gibbs sort of idea?
Yes.
Okay.
Yes, you can.
Thanks.
So you can deliberately, instead of your Gibbs sampler not depending on your current position for that parameter, you can make it flip for that parameter as well.
Nice.
Yes, so here we have the 6 different, so one line, one of these up-down lines is for each of those 6 different weighting functions. On the y-axis, we have efficiency. Again, sorry, I didn't say before, it's minimum over all the components, effective sample size, divided by the number of leapfrog steps. So it's roughly effective samples per sort of unit of CPU time. And we've got K along the x-axis, which is how many apogees do you want to use? 0 would just mean your current one, and then larger values is extra. And the horizontal lines are just showing where the maxima occur. So firstly, all of them rise and fall. So there is some optimum K, or at least empirically, on this 40-dimensional target. Shimon tried this on loads of other targets, similar story to what I'm telling you here. And all of them rise and fall. They might have maxima at different K, but the big take home is actually between the least efficient and the most efficient, there's only a factor of 2. Okay, so at least in the bunch of different targets we looked at, there was only a factor of 2. And in the paper, I do have a heuristic as to why from pi to pi, the flip is only going to increase efficiency by a factor of 2. Okay.
One question. Is the ordering of the lines more or less constant across different targets, or doesn't change much?
It was definitely, okay, so this is for one particular epsilon value. All right, you could choose a different epsilon value. So one thing is, even with the same target, for a smaller epsilon value, your pi tilde, your extended target, your energy really doesn't vary very much. So if you make epsilon really small, your energy is constant. So then modulating according to pi tilde, your squared jump distance, doesn't make any difference. And like the red line and the green line, so here the red line is much lower than the green line, they coincide. Okay, but sensibly, you're never going to choose an epsilon where you've got no variation in energy. It's just not going to be efficient. Too many leapfrog steps. So that's one thing. The ordering of the lines on the targets we looked at didn't change much. So these two sometimes, so these are both jump distance of some form modulated by pi. These were both usually more efficient than the other two. Sometimes just having pi, the black line, was the worst. but you can see it's not much better here than squared jump distance.
Can I ask you
I have a
another
feeling-
question?
Can I just one finish on
Yeah,
this?
go on, please.
Shimon didn't actually look at this, but I have a feeling if you went for some really elongated target, I think this has an eccentricity of 20, so 400, the variance matrix varies by, the eigenvalues vary by. I think if you went really extreme, you might find the flipping is not so good. But yeah, sorry, another question.
Okay, thank you very much. Is any of this curve related to standard HMC?
Sorry, I cannot hear you.
Is any of this curve, does any of this curve relate to standard HMC?
To standard HMC? No, because this is to do with the weight function you choose for sampling.
Okay. So can I ask you, sorry, maybe I didn't understood right. What is the interpretation of the black curve with the weight pi of Z prime?
So the weight being pi, what that means is, if I go back here, you've created your segment, and now you're going to sample a proposed point, right, that you may or may not accept.
Okay.
We're going to choose that according to pi tilde, so the e to the minus Hamiltonian, with the probability of me choosing any particular circle proportional to e to the minus the Hamiltonian at that point.
Okay. So the higher the density, the more likely we're going to propose this state.
Yes, but it's not the highest target density, it's the highest overall energy or lowest overall energy.
Okay, thanks.
So essentially the take home from this was it doesn't really matter too much which one you use. But it actually does, because turns out the first three of them, we can do the whole thing. So naively, what you would think, go back to here, is that you have to store the extended target value and the position and momentum at each of these points. You then sample with probability proportional to the pi tilde over the sum of the pi tildes, and then you do your accept reject. Now, it turns out, you can do your sampling with probability proportional to weight for actually the first 5 of the proposals without bothering to needing to store any sort of set of things in memory. All right, as in the whole set along the path. You don't have to store that. But you also need to calculate this term in the accept reject ratio, and you don't yet know what Z prop is. But it turns out, even with that, the first 3 of these, which is basically pi tildes and squared jump distance, you can do without storing the whole thing in memory. So, and that actually led to quite a computational speed up, because having to store, say, 1,000 points in memory, and these are each 40-dimensional for both position and momentum, was a lot.
And is the intuition behind that just as you're building the path, you can start doing the sampling as you go, essentially?
Yes. So for all the first 5, you can do the sampling as you go, as you're building the path. And that's quite straightforward. But for squared jump distance, if you think of x minus y all squared, you've got x squared, y squared, and minus 2xy, and they can be dot products in higher dimensions. You can store those summary statistics and use them to do the z prop minus z all squared as well. So you can store a finite number of summary statistics and be able to calculate the acceptance ratio too.
Cool.
I was a bit annoyed to discover not the second thing, but you can sample as you go. Stan actually already had come up with that, or the nuts algorithm already used that. Bit annoying, but hey. So the best of the 3, which we can deal with kind of order 1 memory, is modulate by squared jump distance and your extended target. And here's one result. So this is the banana target I showed you earlier. This is what we saw earlier for HMC and slightly blurred HMC, epsilon and L. And here's Apogee-to-Apogee path sampler. You've got your leapfrog step size and the number of apogees to choose. It's quite a banana-y banana, so the number of apogees you need is quite high. But you can see, so the optimal efficiency, first, it's just over 0.012. For HMC, when you blur it, it's slightly bigger. Okay, so HMC in this particular instance is ever so slightly more efficient. But you can see how if you get K wrong, it doesn't matter so much. If you get epsilon wrong, it doesn't matter so much. So it really is much more robust to tuning. And if you look in the appendix of the paper, we've got this for a whole bunch of other targets, just to show that it really is that robust. And why is it that robust? It's two things. So one, with HMC, if you happen to choose something a bit wrong in terms of the integration time, then you're always doing that exact same integration time. Whereas firstly, we've got the randomized thing, and much more so than the blurred. But the second is, and you can see my hands. So suppose your target starts here, your path starts here, comes on, double backs, come along, double back. You've got K totally wrong, and you've done a huge number of paths going like this. You're gonna still sample with probability proportional to roughly the squared jump distance. So the bits you're going to sample from it are the bits where it was, the things you're likely to sample are where it was far away. So I think it's the combination of those two things, the bit of randomness and you're going to sample where it's far away, means even if you get K wrong, all that's happening is a bit more computational cost for doing the extra leapfrog steps. You're not getting to a bad position. And yeah, when we looked at lots more, sometimes HMC was a bit better than the Apogee-to-Apogee path sampler, sometimes a little bit less efficient. So in fact, here's a load of targets. So these first four are all normal. They all have the largest scale compared to the smallest scale is 20 times bigger. They're all dimension 40. And it's just the differences are just exactly how you go from scale of 1 to a scale of 20 over your 40 dimensions. And this is HMC blurred, which it's all relative to that. So here's how HMC does. And in one particular case, it does a reasonable amount worse than HMC blurred. Two cases, actually. Apogee-to-Apogee path sampler, again, once it was a double as effective, but mostly it's about the same. We also put in NUTS. So the NUTS algorithm is automatic, so it's obviously a competitor with our algorithm. NUTS algorithm is a really complicated, messy black box which has functions that call themselves over and over again, therefore sort of piling up on the stack of your computer, or the random variable, the variables you've got. So NUTS does, again, similarly. Now, what we did was pick the one where the Apogee-to-Apogee path sampler does the worst compared to HMC, which is this. So this particular way of scaling the components up from 1 up to 20. And we looked at it in more detail with different targets like skewed normal, logistic, higher dimensional Gaussian, and one even more eccentric Gaussian, because we wanted to try and break it. So we picked the worst it does and then see if we can make it even worse. And we couldn't really. It's never worse than half HMC, well, HMC blurred. And
can I ask you what is the difference between the 4 first lines?
Okay, so if I want the standard deviation to go from 1 to 20 in 40 dimensions, then I could just do an arithmetic progression on the standard deviations. Or I could do an arithmetic progression on the Hessian, on the inverse variance. Or I could do an arithmetic progression on the variance, or I could do an arithmetic on the inverse standard deviations.
Okay.
All right, that's all what those 4 are. So we just tried different ways to see if we could break it, because because it's using where you're going uphill and downhill, it might be sensitive to the shape. But in terms of efficiency, when you're tuning it, it really doesn't seem to be that sensitive. The Rosenbrock in 20 dimensions and 40 dimensions we looked at. Well, that's 40. Radford Neal came up with a target when Nutt's paper was released. He wanted to break it. So he came up with a Gaussian target that breaks Nutt's, or there you go, there's Nutt's, there's HMC blurred. Apogee-to-Apogee path sampler is pretty good. HMC, it fell. I think Radford Neal didn't say this in his blog, but actually it breaks HMC, his target does as well. So Shimon just could not tune HMC. He could not get it to work. If you look at the minimum effective sample size over all components, there's always one that's behaving really, really badly. Okay. Stochastic volatility model, I'm going to skip the details. We wanted to try a proper nasty target. End result, again, relative to HMC blurred, we couldn't tune HMC. Apogee-to-Apogee path sampler is pretty much as good as HMC. If you just, Shimon was interested in what if you just use a single segment, and it's not terrible, even for that, and Nuts is fine as well. Some theory. How long have I got left, Sam?
You've got 5, but you know, we could definitely go up to 10 if you want to take your time. Like, I'm not in a rush.
Okay, well, let's see how I go. I'd like to explain the theory to you because it gives a nice intuition, which really makes sense as well when you see it. So we're interested in this dot product, or I called it momentum transpose the gradient. So the component of the momentum in the gradient direction. And we're interested in when this changes sign from positive uphill to negative downhill. Okay, well, this is a function of your current position and your momentum. So let's imagine that's random, all right, because you could sample a new momentum at any current position, and imagine sampling your current position from the actual target. So imagine you're stationary. And I'm going to look in the limit because it was just, you could analyze it. But we found, you look at an HMC path with some leapfrog step epsilon, and it resembles quite a lot what you see in the limit as well. And we're letting NT be the number of apogees in time t. Then let's consider the usual kind of product target that people analyze, including me, quite frequently. So the potential is a sum of similar terms or with the same function, but we're multiplying. So we're using a different, what's new? New is the inverse scale parameter, sorry, inverse variance, yeah, or squared inverse scale parameter. Yeah, so essentially I've got a product target. Each component has the same functional form as all the others, but a different scaling. And nu is the squared inverse scale parameter, ui, of component I. Then so this is an interim result, this is the main theorem, but if I scale with dimension appropriately, this dot product, then it tends to a stationary Gaussian process as dimension goes to infinity. So why is it even random? Well, it's a random function that depends on your initial momentum and your initial position. So you get a realization from the stationary Gaussian process. So the covariance between this dot product at any two times is some function v that only depends on the difference. And we have a form for it, but it's horrendous. That doesn't matter. The point is what you can do next. So there's a result in the late 60s, I think it was, where somebody found a formula, a general formula for the expected number of zeros in a stationary Gaussian process per unit time. Now, when this is 0, that either means we've gone from downhill to uphill or from uphill to downhill. So it could be a perigee, you're at the lowest point and your momentum is, your gradient has switched signs, or you could be at an apogee. So we can use that result because we know what this covariance function is. And when we plug it in, we can find the expected number of apogees in some time interval t. Now, there's two parts to how I've written this, and many of you will realize, hold on, this bit could be cancelled with some of this bit at the bottom, but I'm deliberately not, because, so this first bit, expected value of nu. So remember, nu is the scaled inverse squared scale parameter. So that square rooting it, you're roughly getting an idea of the inverse scale. Time is proportional to distance, so you just got distance divided by scale. All right, so this is just something fixed in terms of if I stretch every dimension by a factor of 2, then this square root thing here will just halve. If I multiply time by 2, then t will double, and I get exactly the same here. So this is just saying your overall momentum and time compared to the overall scaling of the target. But this is saying, how eccentric is your target? Yeah, if all your news were the same, if all these news were the same, then my target would be not isotropic, but IID. This would be 1. Otherwise, this is bigger than 1. And how much bigger depends on just how different my scales in a different direction are. So this is telling you something that's fairly obvious. The more different your scales are, the more apogees you will see. All right? And it is giving the form for that as well. And it's actually the sort of square of the squared inverse scale parameters. So that was the nice thing that came out of that. It's kind of obvious. You know, if you're really stretched, it's going to wiggle and wiggle and wiggle and backwards and forwards like that. But it was nice to get the form. So I think I'll just mention the tuning diagnostics. So you want tuning epsilon, well, you want to tune till you've got sensible acceptance rate. We don't know the exact acceptance rate, but about 0.8 seems reasonable. But how do you choose the number of apogees, number of segments? And what we discovered works way better than I'd even hoped is you put in a short tuning run where you use a really large K, like 50 or 100. So you've got 100 segments or 50 segments. And each time you propose, when you've actually proposed something, you can have a look at which segment you proposed from. And the segments which are typically further away with larger pi tildes, you will propose from more often. So, you know, further away proposals, you will typically propose from more often because we're proposing in proportion to the squared distance away. Now, if you're sitting your K segments on top of your current segments, very rarely will your current segment be either the last or the first. Mostly it'll be somewhere in the middle. So it's going to be, if you've got K is 50, so you've got 51 segments, it's going to be very unlikely that you'll be 51 segments away, because you'd have to have chosen so that your current segment is the 0th or the 51th, and then propose from the very end. So getting this on its own isn't quite right. You need to adjust for the fact that you're placing a kind of K+1 length ruler over the top of things. But if you do that, and then find the actual segment number, distance away from a current that you proposed from most often, and then do your main run using that, it seems to work really well. And in the paper, there's a heuristic as to why. Here's how it actually does in practice. So these are the 4 different types of Gaussian target with different ways of changing the scale parameter, and various different eccentricities from 10 ratio of standard deviations, largest to smallest being 10 to 40. And Shimon has tried, what did the diagnostic with a massive K show was the optimum K? And when he did a grid search, what was the optimum K? And it aligns so well. I was a little surprised it did so well, in fact. So to sum up, we've got Hamiltonian Monte Carlo. I mean, it's in some ways the method of choice, but even though you can tune your epsilon, Alex Beskos and co-authors came up with a 0.65 acceptance probability for tuning epsilon, but tuning L, so epsilon, that's given total T, but tuning T or L is actually really difficult, and it can go badly wrong. Even when you do some blurring, it's still almost fall off a cliff. Now, there is an alternative out there called NUTS, which does automatic tuning. The epsilon is just standard adaptive MCMC, I think, but the way of tuning T is horrendously messy. And if you wanted to actually make variations on it, you'd need to understand that and then try and make some changes. So I would propose that Apogee-to-Apogee path sampler is actually quite a simple idea. It relies on the fact that it doesn't matter where you start from within a path, that's where in terms of position and momentum you start, you will always see the same set of segments. You'll always partition the path the same. And the tuning is much, much more robust, okay, than HMC. And we've got a diagnostic which works remarkably well. And you're not losing anything in terms of efficiency compared with NUTS. There's lots of other work you could do with the Apogee-to-Apogee path sampler. So if you did keep storing everything, then if one proposal fails, well, you should be able to do a delayed rejection and propose another move. I've not looked at that in any detail. There are alternative ways of proposing K+1 segments. We've looked at one other, there might be others. We could obviously put the epsilon adaptation that's in NUTS in there or something similar if we wanted to. You can also make it properly non-reversible. Yeah, which I've written here. That's definitely something I want to look at. That's it. So thanks very much for listening. Are there any questions?